Hello, everyone. My name is Harja, and welcome to my two-part presentation on my convolution response project. In the first part, I'll be walking you through the mathematical foundation of continuous time convolution and how we can use sampling to derive it. In the second part, I'll be giving a practical demonstration using real audio recording where I apply convolution to simulate my voice in an echoey room. Without further ado, let's get into part one. Every system we study and control our signal processing receives an input and produces an output. For linear time invariant systems, or LTI systems, there are two key properties, superposition and time invariance. Superposition means that if an input x of t can be represented as a sum of smaller signals, the system's total output is then simply the sum of the individual responses to those smaller signals, written mathematically as such. The next property, time invariance, means that if an input signal is delayed by some specific amount of time, the output signal is going to be delayed by the same amount of time, as you can see right here. Together, these two properties make LTI systems predictable and relatively easy to analyze. Now that we understand those properties, let's try to derive convolution. To understand where convolution comes from, we must think about how we can approximate an input signal x of t. To begin, we can represent x of t as a sum of small rectangular pulses, where each pulse has a width of delta and a height of 1 over delta, giving it an area of 1 each rectangle, defined as such. If we translate this into a sum for all of our small pieces of x of t, we can then express this signal as this. Since each pulse has an area of 1, each sampled piece will have the value of x of t at that t equals k delta, as you can see right here. By applying the two properties of superposition and time invariance, we can see how each pulse p delta of the input signal has its own output of h delta with the same time shift applied. We can then represent the approximate output y delta of t as such. Finally, we can take a limit as delta approaches 0 of y delta of t. As we make delta smaller and smaller, the pulses become infinitesimally thin, and the amount of samples becomes larger, giving us a more accurate summation of y delta of t. This sum then turns into the continuous time convolution integral, which describes the output of any LTI system. Now let's look at this concept visually using MATLAB. Here, I chose the input signal x of t equals e to the negative t u of t. I plotted the original signal x of t along with its pulse-based approximations for three values of delta, 0.25, 0.1, and 0.01. As delta becomes smaller, the approximation x delta of t looks smoother and more continuous, eventually almost converging to the true signal. You can see here that for large delta, the signal looks coarse, and as delta approaches zero, it becomes quite the accurate representation of x of t. In part two, we're going to be applying convolution to real audio signals. The idea is to make my voice sound as if it were recorded in a completely different acoustic environment. And so I have two audio files. The first file is a short clip of me speaking in a dampened room, and another recording of an impulse response to a clap in an echoey room. When we convolve my voice with this impulse response, we should be simulating how my voice would sound in that environment. So I'm gonna go ahead and play the audio.
This is definitely a very interesting audio sample. This is definitely a very interesting audio sample.
You can clearly hear the difference that the second or the final recording has compared to the original recording of my voice. The second one or the final one has echo and reverb that is similar to the staircase that the impulse response was recorded in. I don't think the convolution was perfect. However, I do believe that the results are strong enough to showcase the effects of convolution. That's going to be it for my project presentation, and thank you for watching. Bye bye.